This worksheet, section 19.7, is going to walk you through some of the types of problems that you'll be doing on ALEKS that require you to understand reaction mechanisms and rate laws associated with reaction mechanisms. For the first set of problems, we're going to be dealing with this mechanism right here. So remember, the set of steps together is called the reaction mechanism. Each step itself is called an elementary step. So here we have two elementary steps, which we're calling 1 and 2. And then also over here, just expressed, we'll end up using this later, we have the rate constant for elementary step 1 and the rate constant for elementary step 2, and we're using those subscripts to help us distinguish one rate constant from the other. And then also we have some information about K1 relative to K2. That this is telling us that K2 is way bigger than K1. So the first question is asking us to compare K1 to K2. Like, that actually is the answer to the first question. So can I move that down there? Look at that technology, it's so awesome. K2 is bigger than K1, so which one is the slow step? So we got to think about what this means, slow step versus fast step. The step that is slow is going to have a low rate. You can think about this a lot like driving. 50 miles per hour is a lot faster than 20 miles per hour. 50 molarity per second is a lot faster than 20 molarity per second. So the slow step is the one that has the lowest rates. So the slow step for this reaction is elementary step number 1, because K1 is smaller, lower, slower than K2. So let's add, a lot of times when we identify our slow step, we will literally write that with our data slow step, and this is our fast step. So maybe this slow step has high activation energy, something along those lines. Write a balanced equation for the overall reaction. This is really similar to things that you've done before, like with Hess's law, where we are just adding these two reactions together. So we're going to take all of the reactants from elementary step 1, that is NO2 and O3. And we're also going to take the reactants from elementary step 2, that is NO3, and another NO2. So let's change the coefficient for NO2. So those are all of our reactants. And now all of our products. We have NO3 and O2, and O3 and O2. And then we also have N2O5. You know what this reminds me of? This reminds me of when we're balancing redox reactions and we're combining the two half reactions together when we're all done. So also very much like that, we're going to simplify the equation that we just wrote by canceling anything that appears on both sides, left side and right side. So if we're looking at what do we have 2 NO2 on the left, but it is nowhere on the right. We have O3 on the left, but it also is nowhere on the right. We have NO3 on the left, it is also on the right. So that means that we can cancel that term out and simplify this equation. So what we have written here, this right here, after we've canceled out the NO3, that is going to be our overall equation or our overall reaction. Now, the next thing we're going to do is write an individual rate law for the first step of the reaction. So for elementary step number 1, write an individual rate law just like we learned earlier in this chapter. This is going to be in the form, this is where we say rate equals some rate constant times our reactants raised to a stoichiometric coefficient. So we're looking for something that's in this kind of generic form. We're doing this for elementary step number 1. So in order to make things not confusing, we're not just going to say rate, we're going to say rate sub 1. To call it that. And then also same thing with K. Instead of just saying K, we are going to say K sub 1. So rate sub 1 is equal to K sub 1. And the reactant for elementary step 1, we have NO2. And we also have O3. Now, one of the things that is unique about writing rate laws for elementary steps is that in an elementary step, for an elementary step, the stoichiometry of the reaction is the exponent in the rate law. So in the rate law, we are actually literally expressing how many NO2 molecules need to combine with O3 in order for this reaction to occur. The actual number of NO2 and O3 that come together. And that information is given to us in the elementary step, which is why in this case, we do pay attention to stoichiometry. We do not pay attention to stoichiometry if we're writing it for an overall equation, but we do pay attention if we're writing it for an elementary step. So this is the rate law for elementary step number 1. And now we're going to do the same thing for elementary step number 2. This is going to be a rate sub 2. The constant is going to be K sub 2. And let's scroll back up and look at what our reactants are. We have, in step 2, we have NO3 and we have NO2. And both of them have a stoichiometric coefficient of 1. NO3 and NO2. So there's our rate law for the second step. Now it asks us to list the intermediates of the overall reaction. The intermediates, remember, are not products, but they are produced. It's like a riddle. They are not reactants, but they are consumed. They are used. So how is this? They are not products or reactants of the overall equation, but they are produced and consumed at some point during the reaction. They are the substances that we canceled out when we were combining elementary steps to find the overall equation. They were substances that were produced in an elementary step and then immediately consumed in the next elementary step. So for this reaction, our intermediates are NO3, we only have the 1, because it doesn't appear in the overall reaction. So it's not in the overall equation, but it is, yes, in the elementary steps. So anything that is in elementary steps but not in the overall equation, that is going to be an intermediate. Now it asks us to write the overall rate law for the reaction. The overall rate law is dictated by the rate law of the slow step. So this one right here is our slow step. In case you forgot, where did that come from? That came from way up at the beginning when we were comparing K1 to K2. And we said that elementary step number 1 was our slow step. In the last video, I talked about how the slow step is the one that's going to control overall the whole entire rate of the reaction. So we're going to rewrite the rate law of the slow step using just rate and K, not rate 1 or rate 2 or K1 or K2, because now we are writing it as the rate law for the whole entire reaction. And in order for us to be happy with this overall rate law, we have to make sure that it does not contain intermediates. Our intermediate is NO3. Do we have any intermediates in this rate law? Looks like we do not. And since we do not, that means that it is okay. We cannot have intermediates in the overall rate law for a reaction because we don't have the ability to monitor intermediates. We can't control how much of them we're going to start with. So because of that, we cannot have them in the overall rate law. Compare the overall rate law to the individual rate laws in problems 2 and 3 and express the rate constant K in terms of K1 and or K2. So what does that look like? So first we had rate 1 equals K1 NO2 O3. So let's rewrite that down here. Rate 1 equals K1 NO2 O3. And the second thing that we had in problem 3, looks like those numbers are wrong, problem 3 and problem 4. In problem 4, we had rate 2 equals K2 NO3 NO2. Rate 2 equals K2 NO3 NO2. And we are comparing those individual rate laws to the overall rate law, which we just decided up in problem 6. The overall rate law would be rate equals K NO2 O3. And so at this point, what we are literally doing is we're looking at this overall rate law, and let's start by comparing it to this individual rate law. Is it similar? And if so, how is it similar? Well, what I see when I look at this is that the terms NO2 and O3 are present in both of them pretty much identical. And so if I say that the rate of step number 1 is equal to the overall rate, which we said that because that was the slow step, then that means I have the conclusion that the overall rate constant K is equal to K1, because the only thing that's different about the highlighted equations is that in one of them I'm using the symbol K, in the other one I'm using the symbol K1. So what is the point of this? What does this mean? This is just our way of saying that the overall rate constant K is equal to the individual rate constant K1, and another way of saying that the rate constant K2 has nothing to do with the rate of the overall reaction, so it has nothing to do with K. I know this is like, most people at this point are saying, what? What just happened? Let's look at another example, and then hopefully it will be a little clearer.